Hi, I'm George Nardi, Vice President of Aquaculture Services at Innovasea. Thank you for joining us today for our roundtable discussion on feeding strategies to maintain optimal water quality and fish performance. And thanks also to RAS Tech for hosting the event. Feeding plays a preeminent role in water quality for any recirculating aquaculture system, and there are numerous feed-related factors you need to consider when designing and operating your system. We're going to look at those today with our panel of experts who combined have decades of experience in the aquaculture industry. Joining us are two of my colleagues from Innovasea, Greg Beckman, Vice President of Integrated Systems, who serves as our Senior Technical Project Manager and Lead RAS Designer. Chris Manley, a RAS designer whose primary focus is on designing, modeling, and managing recirculating aquaculture projects. And we're also pleased to have Steve Backman of Skretting North America on the panel today. Steve is a licensed veterinarian and currently serves as product manager at Skretting, the world leader in the manufacture and supply of aquaculture feeds, where he has worked for the last 32 years. He also serves as president of Magellan Aqua Farms in St. Stephen, New Brunswick since 2003. So it should be a robust discussion. Let's get started. The format of the webinar will be a 40-minute roundtable discussion, followed by 20 minutes of questions and answers from the audience. So let's get going. And Greg, I'm going to start with you.
Okay.
What's the most important consideration when designing a RAS system?
Yeah, that's a great question, and I appreciate being involved in this webinar. So as a discussion or the topic of the webinar is, I think everyone can understand that we're going to say feed is the main focus, or one of the highest focuses that we look at when designing a RAS system. So, and to step back a little bit from the RAS system, I'd like to talk a little bit about feed globally from a facility perspective, right? So what's our goal? A goal of an aquaculture farm is, we're trying to generate, a high quality protein from a low quality protein, or a high value protein from a low cost protein. So that's kind of the goal of a facility. And to do this, we have to feed that lower cost protein to create that higher cost protein. So feed is a driving factor throughout a farm. Additionally, it all ties into everything. So to get biomass to produce and sell, we have to feed to create that biomass. So there's that correlation between the feed volume that we require, the food conversion ratio of the fish on that feed to create that protein. Feed is also, if not the highest, one of the top 3 highest costs of production, generating cost of production in terms of OPEX cost for the facility. So taking that as a global perspective of how feed plays into the whole thing, we start talking about RAS systems. We talk about this as RAS systems, if you want to think about it, really process feed. They don't necessarily process fish. Right? So feed goes into the system, and those calculations, or the feed rates and their effects, is what drives pretty much everything in regards to how we size the system, manage the system. So think about a recirculating system as processing feed more than processing fish, because it all drives back down to that. As we tell our clients, if we're working with our clients and they're providing us information, or we're developing information with them, is if you get only one number right, when we put into the RAS models, make sure the amount of feed and the protein that we're feeding is the one number that we get right, because it does drive all the other calculations. And then the effect of feed, really. So in the end, the feed drives all the water quality aspects that we're looking at. There's some tie into all these things, which I'm sure Chris will touch base on. And if those factors, are not designed for, or the feed is creating other water quality parameters that are detriments to those, that can, affect the operation of the systems and or the productivity of the farm. So feed, I think feed really is where we want to is the main driver of what we're looking
Thanks, Greg. Speaking of water, how does feed impact water quality in a RAS system? And as a follow-on, how does that affect fish health? Chris and maybe Steve can back him up on the health side of it.
Yeah, sure. And thanks for everybody to have part of me for this webinar. So yeah, going back on what Greg said is when you design or when you're looking at designing a RAS system or you're going out to have somebody else design it, is feed is the #1 value that you want to have, you want to get right. And the reason why is because what's driving your water quality, what's affecting that is feed. So many studies have been conducted to give a design estimation on how feed affects water quality. And what the industry has done is taking the accumulation of all that data and providing what we call, rule of thumb values. And this doesn't just pertain to recirculating system, it pertains to flow through, net pens, pond culture, for how feed affects water quality. So an example of this is, basing off of a kilo of feed will, for example, create about 250 grams of solids. And in terms of oxygen demand, 1 kilo of feed will consume about 1/2 to 1 kilo of oxygen. And that depends on the size of the fish and the temperature of the system. For example, a small cold water fish will have an oxygen demand of 0.5 kilos of oxygen consumed per kilo of feed given. And then as you get larger and warmer, that oxygen demand increases. In terms of carbon dioxide, for every kilo of oxygen consumed, you're getting roughly 1.2 kilos of carbon dioxide produced into your system. So when you're feeding a system, designing a system, you got to be aware of, for every kilo of feed you're putting into that system, you're getting, 250 grams of solids. You're getting roughly 1/2 to 1 kilo of oxygen consumed, and you're getting, roughly 1.2 kilos of CO2 produced. So, obviously that fluctuates between systems depending on, a multitude of factors, but it gives us a good idea of how to manage water quality in a system and also how to design around that. Another important water quality parameter is ammonia. Total ammonia nitrogen is usually how we express that. And that is based on, again, it's linked to feed, but it's also linked to the protein content of the feed. So, protein, and I'm sure Steve will kind of mention this later on into this webinar, but, protein content varies, and it varies depending on life stage. If you're feeding a smaller, fish, you kind of want a higher protein feed, and then it kind of tapers off as the fish grow. So the higher the protein content of the feed, the more ammonia production you're going to have. So having the percent protein content is important. And then roughly around 9% of that protein from that feed is going to be converted into TAN, into total ammonium nitrogen, down the line. So we use these feed rates, we use these production rates, we call them, and we use that to design a system. And then you can also use that if you already have a pre-existing RAS, and say if you're seeing, a spike in TAN that you want to drive down, then you can go and lowering feed rates, and you can manage a system based on knowing these values as well.
Yeah, I think before Steve jumps in on a little bit of the health potential aspects, just to follow up a little bit on the TAN aspect that Chris spoke about, is a lot of people coming in and looking at RAS systems talk about TAN. They provide system designers with TAN, and TAN is an important factor, but TAN exists in two forms, which is dependent. There's ionized and unionized fractions of that, with the unionized being the portion that's more detrimental to fish health. So it's important to work with your system designers to understand what your allowable TAN is. A lot of people will come in and say, I need a TAN of X, Y, or Z. Those values should really be calculated to maintain an unionized value of that fraction, depending on your temperature and your pH of your system. So that is a little bit of an important distinction, I think, to make sure that when you're talking to your system designers, you're talking about unionized ammonia as well as TAN.
Thanks, Greg. Steve, any comments?
Oh, sure. Yeah, yes. First comment is thanks for inviting me, and especially thanks to really recognize the role feed has in RAS systems. When you think of a RAS system, it's really a spaceship for fish with the entire life support system for that animal being contained in a closed system. So anything you put into that system needs to be managed and dealt with from the biological point of view of your animals. And so when you're designing those systems, the key driver to feed use is the output in terms of how much fish protein you want to come out the other end. Because really all that machinery is, as Greg mentioned earlier, fish included, is to transport that less valuable or less expensive protein into a highly valued protein source for human consumers. And so that's the ultimate goal, and the driving factor for that is biomass. And so from a feed perspective, as Chris mentioned, as fish grow, their protein requirements decrease relative to their energy requirements. So we need to be cognizant throughout the system that we balance both protein and energy. And as a rule of thumb, Chris gave a rule of thumb for TAN production, but if you're using protein to provide energy, and animals eat to satisfy their energy demands, 2% of protein roughly equates to the energy you receive from 1% of oil. So it's very easy, if you're under supplying energy, to increase that protein value and generate more TAN through inefficient diet formulation. And the other point is that, as Chris pointed out, protein is the primary source of TAN, and really protein is just a string or a chain of amino acids. And amino acids need to be provided in the right balance to assure optimum growth. Because when you break down amino acids for things like energy, you cleave off the amino proteins, and obviously the amino relates to ammonia. So you're cleaving off that nitrogen component, which is then converted to ammonia and excreted through the gills. So from a fish health point of view, it's really important to maintain those water quality parameters, because fish, unlike humans, their gills are their kidneys. So they diffuse or get rid of their nitrogenous waste by simple diffusion across the gills. So if ammonia is high in the water, there's a less of a diffusion gradient, so fish have more trouble releasing that ammonia from their systems. And similar to oxygen and CO2 exchange, they need to be in a natural environment where those levels are appropriate for the species in order for them to be metabolizing the diets effectively and growing efficiently. So simply decrease in water quality can have a significant impact on the fish's performance. And last point is, as you stress the fish with insufficient water quality, you start to suppress other things and make the fish more susceptible to other problems.
Great. Thanks, Steve. Changing the topic a little bit, what's different about RAS systems with regards to feeding? What makes feeding a RAS system unique or different than other culture systems? Greg?
Yeah, I think Steve used a really good analogy I hadn't heard before, in the spaceship concept, right? So all these water quality parameters and the effects of water quality that Chris went through are present in any production system. So a flow-through system, a net pen system, pond culture, all these things, feed creates these water quality effects in every system that produces an aquatic animal. So what's different about RAS is, as Steve noted, except for a small amount of flushing, in most cases, or even being a tighter system, all these parameters are expressed and retained inside the system. So the system has to be designed to convert or add or remove all these factors, as Steve said, to maintain the proper water quality for the fish. So net pen, you feed, the feed goes through the pen on the ending feed or feces, it flushes out of the system and goes into the ocean. It's not going to express a real reaction on the fish, similar with the flow through race-based system. So that's the main driver in research, is that all that stuff is retained in the system. It's an accumulation aspect. You're not 100% efficient at every pass. So there's a balance and a mass balance equations to determine what you need. So you got to put all that equipment in place to treat all that water to make your spaceship run healthy for the crew, as it were. So, I mean, that's really, you know, the main driving force, I would say, and what's different in feeding. Not to get into all the specifics of RAS, but that is the main difference. So one of the things is the feed itself and the fecal material. The first order priority of the research system is to get those solids out, right? Those solids they stay in the system. As Chris and Steve have said, all these effects happen with the fish processing the feed, and they express those water quality parameters. If the feed stays in the system and is not properly removed, or the fecal material is not properly removed, those things start to continue to break down in the system, and then add another level on top up to the water quality that the fish are adding from the processing of the feed themselves. So quick and rapid removal of solids is a very important, or one of the most important aspects of the system design. So you're not adding more on top of what's already going to be coming through the processing of the feed through the fish.
Yeah, and then also to touch on that, you know, Greg mentioned mass balance, and all the like Greg was saying, all the feeds retained. So you know, you are in a spaceship type thing. You can't go and find new water source when it's not there. So flow rates are critical in recirculating systems. Flow rates is what improves your water quality throughout the system. And how flow rates are determined is what we utilize as a mass balance calculation. So you're in and you're out. And how that is done is it's done based on your feeding rates. Like, you know, everything goes back to feed, but it goes down to your feeding rates. It goes down to the production values that I mentioned earlier, but it also goes down to your removal efficiencies of your equipment. You know, nothing's 100% removal in a RAS system. It's accumulation. So these calculations that we do is factoring in that accumulation of your water quality parameters. So to calculate your flow rates, you take your water quality limits that you want. You know, say if it's 6 ppm of oxygen, or, you know, a TAN of 1 to 2. You take that, you utilize your feed rates, you utilize your production values. So how much does your feed produce for whatever water quality you want to flush out, and then your removal efficiencies, and that's how you can determine your flow rates of what type of flushing does your tank need, what type of HRT or retention time within the tank needs, and that is how, you know, you can determine the flow rates in your system to ensure you have proper water quality, because in a RAS system, flow is what helps improve your water quality. Another difference that you'll see in recirculating systems is how other water quality parameters can affect each other. So, you know, in a flow through system or a net pen, your things like pH, like CO2, they're relatively constant because it's going in and it's going back out of the system. And, you know, a RAS, everything's within the system. So as your CO2 of your fish increases, your CO2 in the water from your fish respiring increases, it drives down your pH. So it makes a more acidic pH, and that affects greatly on your ammonia. So as Greg mentioned, you know, RAS, people contacting RAS designers are like, I want to maintain a TAN of 1. Well, you really need to look at what your limits are on unionized ammonia. So total ammonia nitrogen contains 2 forms. It contains ionized and unionized. The problem, the toxic form, is the unionized ammonia. So, and the percentage of that unionized toxic form of ammonia, a part of TAN, the percentage of that is related to pH and is related to temperature. So the warmer the system is, you have higher percentage of unionized ammonia, and the more basic it is, you have a higher percentage of unionized ammonia. So, for example, if, you know, going back to example, say, hey, I want a TAN of 1. Well, a TAN of 1 in a freshwater system with a lower pH, you know, around 7, and a cool water, you know, you're having an unionized ammonia very, very low, well below the limits of a typical like salmonid, which, you know, is around 0.0125 of ionized ammonia. On the other hand, on the other way of the spectrum is if you have a TAN of 1 for a warm marine system, which has pHs, you know, in the 8s, your percentage of unionized ammonia is much higher. So you actually might be over the water quality limits of unionized ammonia. So that's something to consider as well, is when you're looking at designing, or, you know, even if you're doing water quality measurements and you see a TAN of 1.5, you know, it might not be an emergency. You just have to look at, okay, what's the pH of my water? What's the temperature of the water? What's the percent of the unionized ammonia? Then you can determine if you have a problem or not.
Okay, thanks, Steve. And Greg, while we're on the topic, a quick question came in on ammonia. Is in a purging system, what kind of ammonia is generated there, and any comments on that?
Yeah, I can jump on that. So typically when we approach purge systems, before the fish are harvested, there is a raw feed period, a day or 2 days. The tank is going to be harvested to purge. So typically it's a fairly low production rate of TAN in the purge system if you follow that kind of a protocol. There's still going to be a little bit, but the fish, and Steve, I think Steve's going to talk about evacuation times and processing feed through the fish. So within that period of time frame, I would expect that it's a fairly low production.
Okay, great.
And also, sorry, so just to jump in on that is, you know, for a purge system too, you're not feeding them. So, well, like Greg was saying, you have some ammonia production from their gut evacuation, but also you want to limit the amount of biofilm production on the system, because that's, you know, we're trying to remove all flavors. So those all flavor compounds are based on bacteria that form biofilms. So that's why typically you don't see a purge system with a biofilter associated to it, and you have higher flushing rates. So you're not having that ammonia buildup, because essentially it's a partial recirculating aquaculture system.
Right. Okay. Hey guys, I'm on my next question, Steve. I'm going to ask maybe Greg and Chris to try your video image is a bit fuzzy on our end. If you want to go click out of video and click back in just to see if it straightens that up, it would be appreciated. So Steve, what characteristics make feed perform better in a RAS system?
It's a really good question, because the characteristics of a feed pellet in a flow-through system is slightly different than what you'd want to use in a RAS system. And just to pick up on Greg's point earlier about it's really important to get solids out quickly, and that is most relevant to the feces. So one of our goals with RAS diets is to make a really stable feces, but even a very stable feces is still soft. So the longer that feces rolls around on the bottom or through a pipe before it gets removed, the more leaching and the more it breaks down and releases really, really fine particles, which then tax the mechanical removal systems much more. And actually, and some of these particles are small enough to pass through a 40 micron drum filter. So our goal with the pellets themselves is to make them strong enough and visible enough so they actually can roll around and not have much leaching. So it's a real balance between making a stable, secure, well-defined pellet, but not to the point where its digestibility is impinged, and so you end up feeding more feed to get the same amount of nutrients because you've made a concrete pellet that the fish have trouble digesting. So the real factors that we're looking for with pellets is there's 3 key components for pellets. One is the formulation. So RAS systems like stability, and so we need to have a stable formulation which is highly digestible for the fish so that they produce less waste. We need a pellet that has a matrix which is stable and free of fines, and we need to be able to make sure there is minimum oil leakage from the pellets while they're in the water. I may bring this point up later, but one of the issues with oil in RAS systems is that there is really no engineering method to deal with oil in the water. So oil, especially if you're adding calcium, magnesium, and you have a high pH, those oils can undergo a process called saponification, and they make a thick waxy film that will stick to things like drum filters and pipes and become an issue for their efficiency and require increased maintenance and increased cleaning. And the final characteristic I would say would be the density of the pellet, which corresponds to the sinking rate. If you have a RAS system that has side boxes which draw water off the surface, floating pellets can become a problem because often the feeding activity of the fish will push the pellets to the side and they'll be drawn off quickly into the side boxes before there's a chance to consume them. If you have deep tanks, you want probably a faster sinking pellet so that the pellets can pass through the entire population of fish and you get less variation in feeding activity. So it's really important when you're designing the system to let the feed manufacturer know what the characteristics of those systems are going to be and what the requirements are going to be for pellet density, and they can build that into the program.
Steve, I would also think maybe whether it's fresh water or salt water would impact how the feed behaves in the water, whether it's floating faster.
Absolutely. That's one of the first things our quality techs ask for when we're asking for a diet, is whether it's salt water, fresh water, or brackish, because the density of the water will affect the floating rate of the pellet. So if we produce a pellet sinking in fresh water and it goes to a saltwater system, it will probably float.
Right, that's right.
I'd add one little that might work for people with pet owners. A colleague of mine likes to talk about when they talk about the digestibility of feed. So if anyone on this is a dog owner, which I am, and you've fed different types of feeds, you can definitely tell the difference in digestibility factor in your backyard, right? So I think that's same is it's a very similar effect, but all that stuff, all that extra stuff in your backyard is extra stuff in our water that we have to deal with. So, you know, the feeds are highly important. So it's just a good way I've always thought to equate, you know, the importance of that. So.
Absolutely perfect analogy. And the goal for RAS diets is to make them as nutrient dense as possible.
Okay. Density works in the backyard, but other than by area. Okay. Thanks. Hey, Steve, one quick comment. In general, when we're looking at feed, I'm assuming some of these feeds designed for RAS. Just a quick comment on return on investment in terms of their costs and this added technology that's going into these feeds.
Yeah, well, of course, RAS diets are more expensive, and they're more expensive for several reasons. One is they have, the first is they have a tighter degree of formulation, so less ability to least cost formulate because you need that consistency. And you're aiming for the higher end of ingredients. So you're aiming for those ingredients which have higher protein digestibility, higher energy digestibility, and reduced waste. And we're trying to pack as much into a pellet as possible to keep the FCR down and keep the amount of feces going out the back end down. So that adds costs. And then in order to make sure those physical parameters are correct, there's a huge amount of additional testing that goes on before the feed actually leaves the factories. So that extra quality assurance steps and laboratory testing also adds an intrinsic cost into the pellet design.
Okay,
Yeah,
great, thanks.
I'll just touch, sorry, George, just to follow up on that. I mean, we actually did some work with a colleague and some farmers up in Canada, who were always complaining about, the cost of higher quality feeds from what they could find locally. And some work was actually done to show, to the facts that Steve's saying, the digestibility, that it actually cost them more, the cheaper feed to get the same production rate. So
yeah.
it appears that it's less expensive, but when you take all those factors, it actually proved out to those farmers in the end that it was, it reduced their cost of operation of feed using a better quality feed. So.
Yeah, a good example of that be if you have looser bounded pellets, you get an increase in TSS. You see that TSS increase in TSS, the manager's okay, well, reduce feed. So there goes increases your FCR, which increases your cost.
Yeah, and one of the other things that a lot of people forget about with TSS is the heart of your system is a biofilter, and biofilters produce a substance called biofilm, and that's what the bacteria live in while they're performing this function. And really fine TSS tends to lay down and get stuck because that film is very sticky, and it sticks to the biofilter, and it provides a really good nutrition for heterotrophic bacteria. And as heterotrophic bacteria grow, they tend to displace some of the autotrophic ones, which are the ones that are actually driving the denitrification process or the ammonia reduction process. So you're actually decreasing your biofilter efficiency by having those suspended solids deposit and get into the biofilter. So you're taking a double hit. You're reducing your efficiency to remove those nitrogenous wastes, and you're also increasing the nitrogenous waste. So it's a two-way losing proposition.
Okay, great. Well, as a good segue, this investment in these diets, and we know feed is expensive for an operation. Feed storage, sometimes overlooked by operators. What's the best way to approach feed storage? Steve, Greg?
I think you're muted.
I am muted. Steve, you might want to jump on that.
Okay.
From the feed supplier perspective, there's some certain things that are important to you.
Yeah. So one of the things that first comes to mind is I'm really glad this subject came up here because feed is often looked in the design process as brown pellet in a bag or a dump truck, and it's looked at upon as an inert thing requiring minimal storage controls, and it couldn't be further from the truth. Feed is composed of nitrogen, phosphorus, protein, energy, and carbon, and those ingredients are the ingredients that life needs to grow. And they're also the very same ingredients that microbial contaminants need to grow and fungi need to grow. So if the only ingredient that's missing from that whole scenario is moisture or water. So feeds are perishable, and if they're not stored properly, i.e. in warm conditions with high humidity, there's a really good opportunity for bacteria to grow, and there's a real opportunity for the product to go moldy. And neither of those scenarios are good for fish health, and they're not good for feed efficiency. The other thing that happens is when you add oxygen to that mix, and there's 20% oxygen in air, you have oxidation of lipids and you have oxidation of vitamins. And so you're decreasing the quality of the feed you're delivering. So you're paying top dollar for a feed, and you're delivering something much less if you're not careful with storage. So having the proper temperature profile, good humidity control, and ventilation, and also biosecurity. I mean, you have three things of biologic risk that enter a RAS facility. The first is the in-stocking of the fish themselves. They can bring something in. Your water can carry pathogens and parasitic organisms. And the feed, it's handled by several people. It's coming into a facility, and it needs to be, biosecurity must be taken into consideration when building your feed storage facility. A couple other things that come to mind is having sufficient storage so that you're not threatened by logistics. So as we saw with COVID, a lot of grocery shelves were emptied, not due to availability of supply, but simply because the trucking wasn't available to get the commodities to market. So if you're on a recirc facility and you've only had 4 or 5 days storage or reserve for feed, if something happens to that logistics chain, you could be out of feed and not have animals being starved, and you lose production and you create stress. And so that's not good. So sufficient storage to make sure that you've got enough on hand that you can deal with glitches in the logistics chain. And then an efficient system for racking, so you have first in, first out. So you're not leaving feed to get age and become old, sitting in the back, and then realize 6 months later, oh, we should use that feed, and then you're using older feed and not the newest feed. So it should be a first in, first out system, and then have a docking system and unloading system which is separate from your on-site processing of fish. So that's a biosecurity concern. It seems from an efficiency point of view that have your shipping, receiving all in one spot, but when it comes to things like feed coming in and processed fish going out, you should have them on opposite ends of the facility.
Yeah, those are really good points. A lot of them that I would echo, and we do see that when we discuss clients. You know, a lot of times, you know, they'll come to us not understanding the scope and scale of what a facility really needs to be. I mean, a lot of times, you know, I have a building, I filled it up with tanks. Look at how many tanks I can get in, but they're not accounting for all these spaces. And larger facilities get into larger requirements for those things. So I'd like to echo the first in, first out. We've seen the logistics. So talk about logistics of getting the food to your facility, but it's also logistics of handling within your facility. So, you know, don't have a pallet of feed and get another shipment in, and you just don't move that forward, and you just keep pushing new feed on top. And as Steve said, you end up getting a bad batch of feed that's been sitting there for a while. So it is a real thing. There's a lot of things that clients don't take into, you know, fish handling is usually overlooked in the starting facility design, and feed storage and movement of feed certainly is as well. So
yeah, and even placement of your and even placement of your automatic feeding system. You're obviously going to have feed coming in from a truck, and then you've got either a bins or some kind of loading system. You don't want the feed receiving a mile away from the actual feeding system. So you want to be able to efficiently load feeds into the feeding time and save labor.
Right. Okay, let's move on to an important question that this wouldn't be complete without addressing. What's the best feeding schedule for fish in a RAS system? I know there are options, and what are some best practices? And this is really a question for everybody, starting with Greg.
So as a RAS designer, we're a very big proponent of, you know, a full extended 24-hour feeding day if that's possible. I mean, in some systems it's not in terms of brood stock systems, but to the extent possible, you know, we're looking for a 24-hour feeding day and a feeding schedule that will allow us to do that. And from a RAS perspective, everything's driven from the feed, all the calculations, all the water quality effects. So sorry, I keep trying to get in a spot where I don't have the sun on my face. But you know, 24-hour feeding day, just from a RAS perspective and not necessarily the fish perspective, limits peaks and valleys. It limits the load on the system from having these really large spikes. So the system can process this on a static, ongoing basis. You get into some short feeding days and some tight feeding windows, and by theoretical calculations, if you look at the feed expressing and the calculations based on feed, if you had a 12-hour feeding day, the actual calculations would tell you your flow rate has to be twice as much as a 24-hour feeding day. Now there's some factors that don't make it quite that, but that's generally the effect. So extended feeding day to the extent possible is really beneficial from the system design perspective. And it's also, there's a lot of he's got some things I know he'll probably touch upon, from the fish perspective as well. So.
Okay, so yeah, if I can jump in there. Greg nailed it in terms of feeding strategy. In a RAS system, you really would like that curve to be very flat. So just like COVID, we want to flatten the curve. And that takes a huge burden off the system itself, but it also takes a burden off the fish. And fish are very trainable, they learn. And so if they know they're only going to get 1 or 2 meals per day, and it's a very peak, they know they have to be really aggressive at getting that at feed. So it looks impressive to people watching them feed because they boil the water. But a lot of that boiling activity is not actually feeding, it's aggression. So they're nipping at each other's fins and they're pushing each other out of the way to get at that food supply to make sure they get fed. And what tends to happen is you tend to have a diverging population of fish size. So you have the big bullies and the big guys pushing the little ones out of the way and getting the feed, and you're not getting the feed delivered efficiently, and they're not getting fed to satiation. Whereas if they know that at any time in the day there's going to be feed pellets available and they don't have to be so aggressive, they tend to be a lot more relaxed and they tend to eat more in general, and they tend to have a less of those peaks and valleys in terms of oxygen consumption, CO2 release, and ammonia production. And so it makes it much easier for the biofilter to handle it. It makes it much easier for the mechanical filtration systems to withdraw the feces and the waste. And if you're monitoring that closely, you shouldn't have any waste feed going down the drain. So you should be having some kind of feedback system, whether it's cameras or whether it's people standing at the side, making sure that the feeds aren't being fed too quickly, because a lot of times people will underfeed fish but overfeed them at the same time because they're feeding at a rate faster than the population is eating them, and the pellets then end up going down the drain or out the side. And so your FCRs suffer and your feed costs go up, and you think you're feeding them enough because it's what the calculations say they should be eating, but you're not taking into account what's going down the drain.
Yeah, and a quick follow-on to that aggression aspect, it does look impressive and all that, but other than the divergence of the thing, that's also a spot for physical damage to the fish themselves, right?
And skin infections.
Yeah, so to get them into that relaxed feeding rate is important from all those factors. So especially from a physical damage, and then the secondary stuff is leading to that from a health perspective. So
yeah, and to elaborate further on some best practices, one thing of importance is to make sure you have accurate biomass estimations within your systems or within your tanks. Regular sampling, know how the weight looks like, and keep good count of how many fish you actually have in there so you can estimate your biomass, and to ensure that you are feeding based on what that biomass is. You're not overestimating your biomass, you're overfeeding or underestimating and underfeeding your fish. And another thing too is in terms of feed rates, you just don't blindly feed off of a feed curve or an assumed FCR. You always have to, especially if you have an automated feeding system, you don't just set your feeding system and then just walk away and assume that all the fish are eating or anything like that. You need to monitor feeding events, make sure that they're feeding the feeding slow enough so everybody's getting fed. And that's a good way to determine problems as a manager. You throw a feed in, or you see a feeding event, they're not feeding, or they're not feeding as they're supposed to. You can determine if something else is wrong with the system. And then you can also, during these feeding events, while you're observing, either by doing some hand feeding or observing during a feeding event, you can say, okay, well, they're not feeding as much as what I'm giving them. Okay, we need to tail it back down so that we don't have a lot of excess feed. Or hey, they're feeding aggressively, they need more, and then you can increase your feeding based on that. Another thing too is stick to a schedule and set a schedule and stick to it. We're always trying to, as Greg mentioned, we're trying to do a 24-hour feed day. So if that's your schedule, you feed every, 12 times a day, every 2 hours. Maintain that schedule, maintain that time of feeding. You don't want to change anything. So if you're feeding from, 12 times a day, you go to 4 times a day. That's going to put a change on your system. It's going to put an increased load on the system. It's also going to affect the fish as well. And, we talked about 24-hour feed days. Well, as an operator, you're like, well, gosh, am I going to have somebody there, 24 hours feeding it? And, broadcasting feed every 2 hours, it's labor intensive. So when you start doing, if you're looking at larger systems, especially even smaller systems as well, automated feeding is a good option to divide out your daily rations to make sure you're spreading out your feed and not being labor intensive while doing it.
So speaking of automated feedings, and I think this will be our last question before we go to the audience questions. What are some of the pros and cons? Obviously with larger systems, like you just said, Chris. I think automated feeding systems are a logical next step. And so, how does that fit in? Steve, could you start us off?
Yeah, the pros are definitely much more than the cons. And actually, one of the things that drove the early adoption of the automated feeding systems on the aquaculture industry was the number of lost days to employee injuries from a condition called fish feeder's elbow, which is really the equivalent of tennis elbow, but that repetitive motion injury was one of the first real ones that was documented in aquaculture and created quite an issue. And so that really favors, just from a personnel point of view, you're not having somebody stand beside a tank all day burning out their joints. So that's a definite pro. The second thing is like Chris pointed out, fish are very trainable. They adapt to their situation and they get to look forward to it. So just like my Labrador gets up every morning at 7:30, he's looking for his ball because that's his frisbee time. The fish almost by clockwork train themselves to their feeding time. So you need to be very consistent in the order you feed and how you feed, and automated systems are really good at employing that consistency. They're also very good at distributing feed. If you have inexperienced feeders, often they don't distribute it properly across the tank. So you're not feeding the whole population. And the newer automated systems are very, very good at giving equal distribution across the surface of the tank. As mentioned earlier, it reduces man hours, but it also tracks the data. And data is your biggest asset in terms of managing feeding. If you don't, as Chris pointed out earlier, people like to use feeding tables. I generally discourage them, except as a benchmark, because feeding tables are averages of averages of averages of averages of the whole species, and they are broken up in 2-degree increments typically, or 3-degree increments. And so they have quite a variation. And so if you're in between those, you really don't know where you fall. And the second thing is, if you actually observe individual fish feeding with the camera, those individuals vary every day. So they may eat a lot one day and not eat at all the next. And that variation is captured in the averages, and that can really lead you astray. So you can be potentially underfeeding or overfeeding if you follow a table exclusively. So by using the technology, you get the feeding data, and if you have a built-in feedback system or you're observing it, you can adjust that feeding system to match the feed so you're not wasting or you're not losing growth. So that would be my biggest pros to using an automated feeding system. And as soon as you get up to any scale, there's no physical way you can get the people to do it efficiently. The risk is people tend to install an automated feeding system and then forget it. And they forget that it's a mechanical system that has wearing parts. It's usually installed in areas where there's high moisture and a lot of traffic and dust. And so if you're not maintaining that, you can actually heat the feed up to a point where you start leaching oil, and so you're spraying oil at the end of the nozzle. So it's important to utilize those systems, but it's really important to follow the manufacturer's maintenance program, because that can really start to impact the feed quality, as you don't want to turn into dust, and you don't want it to leach the oil out of it as it's spraying it.
And the final comment that I would have on that, we're proponents of automated feeding because we're proponents of 24-hour feeding days. There's lots of feeding systems out there that can be done. I think the interesting point is a scale issue, as Steve said. So at what point does automated feeding, which can be done at any scale, turn into automated feeding with automated distribution? There's a certain level of scale where capital costs of moving the feed to feeders, the automatic feeders, it would be cost prohibitive, from a production standpoint, but there's a fine line probably there. So automatic feeders can be utilized at any scale. Feed distribution is a little bit different.
Yep.
You're on mute, George, I think.
You're muted.
Excuse me. Guys have any comments on manner of distribution? Air driven. Steve, you mentioned temperature, so you got to make sure that's not high temperature air coming out or mechanically pushed. Is any comments there?
From my perspective, I think I'll turn that over to Chris and Greg, but for me, it's if the system is functioning properly and is maintained, whether it's buckets or whether it's air, or even, I think there's still some water systems around. I think that's less important than how well the system is operated.
Yeah, conversely, I would have asked Steve, from a feed formulator or supplier's question, our goal is to get the feed there in the best quality. So he said non-mechanical breakdown, creating fines. Fines are a huge issue for RAS systems. So Steve said most of them are taking that into account. So.
Yeah.
Okay. Hey guys, well thanks. We could talk for a long time on this topic, and I thought we'd have a lot more extra time, but we don't have too much time, and I'd like to get to some questions here. We've answered a couple of them along the way, and let me see. The question regarding salmonids in a RAS system, and I think we touched on this, but is a floating or a sinking feed preferred?
Steve, you want to, or
Well,
in general, a slow sinking feed would be our preference.
Slow sinking is certainly the one that we sell the most of. Most people have moved away from floating feed simply because you can't put as much nutrients in it. It's much less nutrient dense pellet because you need air in there, and that takes up nutrient space. And the second issue is many of the systems employ side box drains, so top drains to skim off the surface water, and that often skims off the floating feed as well.
So that makes it even more important that in the design you have a good self-cleaning functionality of the tank in terms of flows and getting that material off the tank bottom as quick as possible, I imagine.
Yes.
Absolutely.
Yeah, and unlike a net pen where you're monitoring, you're using floating feed to monitor feeding rates or feeding activity as well. In a RAS system with slower sinking feed, it's easier to manage, easier to see and visualize how the fish are feeding. Utilizing a feed, you don't really need the floating feed there.
Yeah, and the other thing, just from a fish point of view, is if you've got floating feed on the surface, that's the only place that the fish can get the feed. So they're going to be pushing each out of the way to get to that feed. Whereas if you have the whole water column for them to feed, if they're used to feeding in a very relaxed way, they'll stay in their position in the water column and wait for the feed to come to them. They get lazy, and that's good.
Another question that we talk about is there any difference in water quality management practices for plant-based diet versus a fish meal-based diet?
That's an interesting question. So, big rule of thumb comes out, been around CO2, and that to me looks Steve may have some better that. I think more of it as a protein content, and maybe that's not the right question. But we know with protein content, and I can't speak maybe as well as Steve in terms of the type of protein, but from a protein content, the higher the protein, the lesser the rate of CO2 is produced on a unit basis. A lot of people just use the standard 1.375, ratio of CO2 to oxygen. But when you look at the respiratory quotients, at a higher protein, protein is a lot better than oil, and oil is a lot better, than carbohydrate. So we actually utilize a lower CO2 production rate as the protein, and the quality of the protein goes up.
Yeah, I would treat the plant protein the same as, protein based on fish meal in terms of system design.
Yeah, I would too. Like the difference there, the source of protein, it's still protein and still a chain of amino acids, and the fish still cleaves those down to the individual amino acids, absorbs them, and reassembles them according to its own DNA. So I wouldn't see any difference in the protein source in the diet, whether it's from fish meal or whether it's from plants.
Okay, another question that's interesting. We talked about ideally we'd have a 24-hour period to flatten the curve, so to speak. In operationally, what concerns do we have if we're spreading that feed out over 24 hours, and on any individual feeding, do we risk not putting enough feed in to create aggression and competition for that smaller level of feed per feeding?
No, we really haven't seen that if you're feeding them close to satiation. Again, the fish learn that there's feed coming, and they know they're going to get fed throughout the day. So they're much less aggressive, and they tend to relax much more. And if you're doing it right and you're monitoring every day and adjusting, the fish will almost, like I say, wait for the pellet to come down to them, and they just grab it as they're swimming by, rather than actively seek out for it. And you can observe fish behavior if you really want to look down on top of them. If you see the number of fish in the population making S-like curves, so that their heads swinging side by side, that's a fish that's actively foraging, and he's hungry. And so if your feeding practices matched up with the fish, you'll see very few of those fish with that S swimming behavior, and they'll be mostly lined up and stacked in a very consistent pattern.
Yeah, and I did, I personally did research on aggression and, feeding frequency versus, feeding satiation. And it's somewhat species dependent, but mainly it is, you feed right where you try to match the gut evacuation time. So they evacuate their guts, you do a feeding, but also you feed to satiation. So increasing in feeding frequency, and but when you do that, you're hitting satiation as well. It decreases aggression, but it also decreases cannibalism as well.
Now, I want to make a clarifying point about the 24-hour feeding day. A 24-hour feeding day is not 2 feeds 12 hours apart either.
That's right, yeah.
So you have to be within a certain amount of time. That's a little species dependent, but within the gut evacuation period, the time that they're processing the feed, that's the maximum window of time. Times number of feeds to get to 24 hours, because 2 feeds at 24 hours or 12 hours apart is, going to create a very similar pattern to a 12-hour feeding day. So.
Right. So another quick question. Could the flow rate of RAS ever be fast that could affect swimming? And I think this might go to velocity versus volume or energy damping. So Greg or Chris?
Yeah, I mean, so you can manipulate the velocity within your tank based on the inlet orientation or the whole orientation of your inlet pipe. So, there's been a lot of research out there on, ideal swimming speeds for, mainly towards salmonids, and you're looking like in the range of, 1 body length per second, I believe. But, if you have a quick turnover, if your mass balances say that your HRT, your retention time in your tank is, 15 minutes, you can adjust the velocity of the tank itself by manipulating the inlet orientation of your inlet pipe to your, you can move it out to slow it. You move it more perpendicular to the wall or parallel to the wall to increase it. So that's another important design consideration is, for that you want to manipulate that pipe or those holes for that inlet pipe. So, if it's PVC, never glue that section of pipe so you can manipulate it.
But George, I think he hit it right. I mean, there's definitely a HRT and a spin and a velocity. So as Chris said, the spray bar is one thing, manipulating the holes in the spray bar, manipulating the percentage of flow off the bottom versus the side box. These are all physical parameters that, could allow for a high tank exchange rate, but not, turn the thing into a giant vortex.
Okay, guys, I wish we had more time, and I apologize to the audience for the questions I couldn't get to, but I hope most of them were answered during the discussion. So I see we're at the 1 o'clock hour. But that went fast, and I thank the panelists and thank you, audience and RAS Tech for the webinar.
Thank you for allowing us to participate.
Yeah, thank you, everybody.
Thank you, everyone. That was great. I learned a lot.